All right, everybody, here we go. Week 14, day number 2. Yes. Okay, so we have gotten to the point to where we're kind of looking at a few more advanced algebra concepts. Okay. So if you are, let me just say that, a few more advanced algebra concepts. If you are teaching, or if you want to teach high school math, you probably have to take some linear algebra classes with us. You might be asked as an elective to take abstract algebra, or some of your degree plans may require abstract algebra. So as you start working on some of those things, you might hear some words like groups, rings, and fields. So these are actually some pretty high level, especially rings and fields. As you get into those can start being a little bit high level, and they're not tough. They just require a lot of knowledge of the definitions and properties that we talked about in day 1. So for our purposes, we're just going to focus in on groups. We're not going to deal with these other two, but if you get into a linear algebra class or an abstract algebra class, just know that, it's not as bad as it seems always in there. It's really about applications of these properties that we've talked about, and those properties, most students learn those in about middle school. You'll see associative, commutative, all that in the middle school curriculum. So it's not terrible, it's just a really interesting application of those properties. So we want you to know it's out there. Okay, for our purposes, we're going to focus in on group, and we're going to give you this definition. So a group will consist of a given set, an operation, with the following properties or characteristics. Let's call it characteristics. All right, so characteristics. Okay, so what we're going to say is that if we're given a set and an operation, and we know that that set and operation have these characteristics, we're always going to call it a group. That's why earlier when I was saying the word group, when I was talking about sets, I said, I'm sorry, I really need not say groups, because we're talking about sets of whole numbers, sets of integers, things like that. In that case, me using those two words interchangeably kind of gets us in a little bit of trouble. That's why I tried to correct myself on day 1, so we weren't doing that. But this time we are going to use the word group. So number 1, whatever set and operation we have needs to have the associative property, and that needs to work in that particular group. So the group being the set and the operation. So it's going to be a group if that works, associative, which means grouping doesn't matter. Whichever way I put them, I'm okay. Number 2, the set is closed on the operation. Okay, so we'll say the set of whole numbers is closed on the operation of addition, like we said earlier. So we're going to have closure, right? That's what that was called, closure. Number 3, there is an identity element for that particular operation and that particular set together. Okay, now we know from day 1 that subtraction and division don't have identity elements, right? They're not two-sided. They're only one-sided on their identity element. So you can't necessarily use subtraction, which is going to be, or you can't necessarily use division, which is going to be great for us, right? So we don't like those two anyway. They're complicated. And number 4, each element in the set has has an inverse, and here's the kicker, that inverse is also in the set. So it can't just have an inverse, that inverse is also in the set. So if you remember, whenever we did division the other day, we said like 2 divided by 3, those are whole numbers, but whenever I do that, I get 2/3. That's a rational number. So even though we might have some number that could be the inverse for all of my stuff in division, it's not going to end up working out in that particular case because I started with whole numbers, I ended up with rational numbers, right? So it kicked me out of the set. So it's kind of like my inverse is also closed inside of my set, if that makes sense. So those are the 4 properties we're after. So those are the 4 things we'll check for all the time. And if those 4 all work, then we'll call something a group. Okay, so it's a very specific algebraic term for my upper level algebra people. Okay, so the notation is going to look kind of weird maybe, not too terribly bad. But if we're talking about this stuff, we start with a set and then an operation. And they'll be in parentheses, so it might kind of look like an ordered pair, something like that, or maybe interval notation. So you just have to know, whenever we're dealing with these upper level algebra concepts, that's what we're talking about, is a set and an operation. That is my notation whenever I'm dealing with that. So here we go. Here's an example. What I want to know is this guy, I, comma, plus a group, is I, comma, plus a group. So, I don't know, how do we start? What's I? I is integers, right? Okay, I is integers. So, we're talking about integers with addition. That's what we're talking about here. So get that into your head, integers with addition. What set are we talking about, and what operation? So this is integers with addition, and remember that, let me throw this up here, integers was right here, natural numbers, whole numbers, and their negatives, right? So somewhere in your notes you should have that. What was an integer? Natural numbers, whole numbers, and their negatives. So I'm saying whenever I look at that and I'm dealing with addition there, can I hold these 4 properties that are up here? Do they hold true with that particular grouping? So number 1 is associative. So what we want to know is when I add an integer to another integer, and I move around the grouping, does the grouping matter? So maybe it's something like 2 plus -3, because that's an integer, plus, I don't know, -5. Is that the same as 2 plus -3 plus -5? Okay, so this would be -1 plus -5, -6. And this would be inside the parentheses, -3 plus -5 is -8, plus 2 is also -6. Yeah, that one works. So, and again, we know that addition is a really flexible one. Addition's really flexible, multiplication's really flexible. So yeah, I think that this one works. You might need to convince yourself a little bit more, but try it and see. Okay, so that one's okay. Number 2. Is it closed? Okay, so go back and look at your definitions if you need to. If you're not sure, remember that this was, you have 2 particular numbers. Let's do 2 plus -3. We're adding them. They're both integers. And when I do this, do I get an integer? 2 plus -3, I get a -1. That's also an integer, right? So is anything going to kick me out of integers? And the answer is no. 0 was the weirdo, but 0 worked out. So it is closed. Do I have an identity? Number 3. We said that addition always has the identity of 0. So pick an integer, it doesn't matter. -3 plus 0, I still get a -3. So that's a yes. And then the last one is, do I have the inverse? And be careful, is that inverse in our particular set that we started with, in the original set? So it's kind of like the inverse is closed into the set with me. So remember, for addition, like for instance, if I had 3, then his inverse was -3. That got me the 0 back, right? And the question is this inverse guy for that original integer also an integer? The answer is yes, right? So it was whenever we were doing multiplication that we ended up being rational instead. So this is just negative numbers, basically, or negatives of the original opposites. And we're in integers, and so yeah, that works. Okay. So go back to the original question. Is I comma plus integers on addition, or addition on integers, is that a group? The answer is yeah, all 4 of those worked. So it's a yes. Okay. So that makes sense how you're going to work those problems? Yes. I hope. I've got a couple of examples, and really this is all we're doing for today, so hopefully this runs pretty smoothly. So there's one example. Make sure you understand it. We're going to go on to the next one. All right, so yep, that's a group. All right, next example is, my group is Q comma X. Q comma, and that's multiplication, right? A group. All right. Well, hopefully we remember what we talked about the other day. Number 1, associative. Grouping doesn't matter whenever I'm doing multiplication with rational numbers. Q is rational numbers, right? So remember, that's my set that I'm talking about. Rational numbers, multiplication. So there's my set. There's my operation. Okay. So multiplication and rational numbers, yep, associative, grouping doesn't matter. Everybody agree? Yep, it works. Number 2, is it closed? Well, let's think about that. I multiply a rational number, a fraction times a fraction. Do I get a fraction? Fraction times a fraction, do I get a fraction? Yes, I do. Okay, so think about it, work on it if you're not sure. Number 3, is there an identity? Well, when I multiply something times something else, when I multiply something times this element, let me give myself something, and I get that number back, yeah, that would be 2 times 1, right? So that's a yes. I have an element, an identity element. Okay, so last one is the inverse. We're doing really well here. Okay, so I need something that I can multiply by that number. Let me give the example over here. Let's say it's 1/2 times something, and that will give me the identity element, right? Well, 1/2 times, what would that be? 2/1, right? Or a 2. And so what I need to know, this is the trick here, is it's not just got an inverse, we know it does, but we need to make sure that that inverse is also in my set. It's an element of the set. So is 2 an element of the set? Yes, absolutely. That's okay. Okay. Oh, I don't want to put that here yet. Let me put it here. Sorry. Okay. What about if I have some weird stuff going on? What if it was some number that I multiply by, but it wasn't a whole number there whenever I did it? So 3/2 times something gives me 1. What would that be? The inverse for that particular number would be 2/3, right? That's okay, because 2/3 is also a rational number. So, all right, what if it was like weird things? What could throw me off? So sometimes 1 might throw me off. 1 times something gives me a 1. I think we're going to be okay in this case, because 1 times 1 gives me 1, right? And that's also in the rational numbers, so I'm okay there. So what else might be my problem child here? I've mentioned it several times. 0. 0 might be your problem child, right? So 0 is actually just 0, but I can also write, so I'm trying to figure out 0 times what gives me a 1, right? That's what I'm after. So it could be 0 over 1. That's okay. You can really put 0 over anything. It'd be 3, -2, whatever. It doesn't matter. I'll still get 0 on the top. But here's my problem. Whenever I go to multiply by something and get a 1, what would this have to be in order for that to reduce out and give me a 1? 1 over 0, right? Okay, and not only is that not defined, I don't know what the heck 1 over 0 is right now, but we know you can't ever divide by 0. That's a problem. This is not an element of my rational numbers, right? Not a rational number. We don't even know what the heck 1 over 0 is. It's undefined. So that guy, even though all these rest of these worked, that guy, the 0 guy, is a problem. So no, because 0 doesn't have an inverse. And in fact, it's not an element of the set. Okay, so one of the properties did not hold for me, this guy right here. So what do we think about rational numbers and multiplication? Is it a group? No. So not a group. The reason why is because 0 is a bad guy. He's the bad guy here. Right? Okay, so even though everything else worked, that one did not work, so we're kind of stuck. Okay. All right, so there you go. Everybody's good with that? All right, the other thing that might happen when you're looking at some of this stuff is you might end up in a weirdo group, and we've seen some of this stuff when we did the base stuff last week or the week before. We talked a little bit the week before the exam. We talked a little bit about modular arithmetic, right? There's something that's called Z's, Z2 for instance. Z2 would be basically whole numbers where we're talking about mod 2 basically. So I would have, if I was in base 2, 0s and 1s, right? Okay, so Z2 would just be the set of 0s and 1s. And we talked about this when we were talking about modular arithmetic, right? Okay, so we did some of that. For instance, you might have Z5. What would that be modular arithmetic-wise? What numbers could I be working with? It's like a base 5 number, so I get 5 digits. So I would have 0, 1, 2, 3, and 4. Hopefully that makes sense to everybody. Okay, so that would be called Z5. Okay, so we've already talked a tiny bit about the modular arithmetic when we did clock arithmetic, the last week's worth of full information. So we're going to use some of those sets. Okay, there's the set notation. Its elements are 0 and 1. And we're going to use that to see, can we use something that's not necessarily completely natural for us? Can we push ourselves a little bit and say, oh, can we do this and see if we know the group rules? Okay, so the question that I'm going to use is Z2 comma plus a group? Okay, so here my set would be the set of 0 and 1, right? and the operation would be addition. Is that okay? So making sure that you can read this notation is part of the battle, right? So we're just going to use something that's kind of familiar to us with the modular arithmetic and see if we can use our definition of a group here and check it out. So, but the process is going to be the same. It's all about associative. The problem is when I'm dealing with modular arithmetic, maybe I might want to go ahead and do one of those operation tables that we talked about the last time around. So let me do that. It's not too bad. The operation is addition, and I've got a 0 and I've got a 1, right? And going this direction, I've got a 0 and I've got a 1. So it's not horrible. We need to do 0 plus 0, that's a 0. 0 plus 1 is a 1. 0 plus 1 this direction is a 1. So far I'm all right, and I'm still inside of my base 2 type numbers, but I've got a little bit of problem with my modular arithmetic here. 1 plus 1 would be a 2, however, we're in mod 2, so I don't have a 2 in my element, so I can't label this 2. So what happened in base 2 whenever we hit 2? Yeah, it became the number 1, 0, right? Or we said, how many 2's can you pull out of that? I can pull out one group of 2's, and what's the remainder? There's a 0 left over, right? Okay, so as a base 2 number, that would be 1, 0, base 2. So the 0 is what's left over. All right, so we did these the last round of notes. So hopefully you're okay with that. Hopefully you've done that. You know what all we're talking about there. All right, so let's talk about associative. Okay, so associative means grouping doesn't matter, and we're just doing addition here. So you can do some problems if you want to, but it doesn't really matter when I'm moving around the parentheses, right? We know that addition is associative, so that's okay. No worries. Oh, that was number 1. Number 2, is it closed? Well, in fact, the modular is definitely closed, right? Because the very definition of modular means, hey, if I do something and it throws me out like it just did a second ago, I had a 2, which is not in my set, it doesn't matter. We're going to dump the 2 and we're going to go back to the 0, right? So we just do that big cycle all the way around, go circular. So by modular arithmetic definition, yes, it's closed. No worries, right? Number 3, is there an identity? So let's think about this. Is there some number that I can add, because we're doing addition, to the 0 and get back the 0? Well, it'd be a 0, right? Is there some number I can add to the 1 and get back a 1? Well, it would be a 0, right? And you can actually see that identity thing coming in here and here. Okay, so yeah, it's 0. So the answer is yes. Check. Okay, so the only one that's kind of tricky for us, again, that stinking inverse. Let's be careful about it. The inverse, and what we're saying is, now let's remember what inverse really means. If I take one of these numbers, let's start with 0, and I add it, my operation is addition, to some number, 0 should have some number that I can add it to. Can I get back the identity, and in this case we said 0, right? So is there something that I can add to 0 to get back a 0? Well, for 0, it would be 0, right? And that's okay because 0 is an element of my mod here. So I'm okay there. So we need to do that also with the 1. Be really careful. Is there something that I can add to the 1 and I get back a 0 because I want that identity element there? That was a check. And here we go. We did it, right? 1 plus 1 gave me a 0, so it was 1 plus 1. Gets me back that identity element because that pushes me over into the next group of 2's, right? So, hey, it's kind of interesting because I have something weird happening here. 0 is its own inverse. Well, that's in the group, so that's okay. And 1 is its own inverse, right? But 1 is also in the group, so that's okay. So this guy is an okay number. He's in my original mod. So when I say that, yeah, I have inverses and they're both in the group, so that's okay. So what do we think? The answer here is yes, it's a group. It is a group. So actually the modular math kind of stuff is pretty cool. It's enjoyable to me as long as we don't get too big on the mod. I would probably never go above like a mod 5 to you, maybe 6, something like that. Because it just, you can imagine if I had done this table, this addition table, but gone all the way out to 4 and gone all the way down to 4. And just the fact that I'll have to rotate through and look at the remainders on bigger numbers, it just gets a little bit cumbersome. So be aware that those are out there, the mods. You're going to see them in the homework. You're going to have a worksheet. Yeah, so there you go. That's it for today. I told you that day 2 would be shorter, so not too bad. I'll be back with the housekeeping video, and then we'll be done with new material. Oh my goodness, completely done. That's amazing. See you soon.